Nice. Okay. So you begin. Great. Yeah. For some reason, the recording notification is right in the middle of my screen.
Oh.
Now I'll continue. Okay. So last time we discussed Dirac's magnetic monopole, and we discussed how it's a singular solution. You had to sort of put in the singularity by hand, and you couldn't, for instance, compute the mass of that monopole, and you just didn't know like what it's made of, so to speak. Like if you talk about electric charge, we know that if we couple, say, fermions or even charged scalars or something, we can write down, a current and a charge density. And so it's like we know what the charge in some sense is made of. It's made of some composite operator of the fermions or of the charge scalar or something like that. The question is, what are magnetic monopoles made of? Like, is there some physical system in which they are instantiated? And that's what tHooft-Polyakov managed to find. But they managed to do this in the context of the Georgi-Glashow model. So we'll stick to the bosonic sector. So the bosonic sector is an SU2 gauge field coupled to a fundamental Higgs. So let's take the gauge group to be O3, and just so that our visualization of the internal space is simple. The alternative is you take SU2 as the gauge group, and then you have triplet Higgs. So the Higgs is in the adjoint representation. But here you could just have a fundamental Higgs, and you can sort of visualize everything that's happening in the internal space pretty easily, because it's like O3 as though it was, what we're used to. So the notation here is that W with the hat over it is the gauge field for the SU2 theory, or for the O3 theory. And the reason why there's a hat over it is to indicate that it's a vector in internal space. It's a 3-vector in internal space. It's a space-time 4-vector. That's the mu index. But the hat, the vector symbol over it tells you that it's like a internal space 3-vector. Right? Because it transforms into O3. Same with the phi's, the scalars. But you see, the scalars are space-time scalars. That's why they have no space-time index, but they still have an internal space vector symbol. And the cross product here is really the cross product in the internal space. Acts just like you'd expect, with an epsilon. And the reason we write it this way is that if you think now about, say, the structure constants in the Lie algebra of SO3, it's going to be the epsilon symbol, right? So when I have the term in the curvature that looks like the commutator of gauge fields, then it's going to involve the structure constants. So the structure constants are the epsilon symbol, and that defines the cross product also. So that's why it's just the cross product. But just to be clear, it's a cross product in internal space. Great. And we have finally the potential, which is a Higgs potential, right? So a metastable potential. Quartic, and if we went and looked for its, for its minima, we'll find spontaneous symmetry breaking solutions. Now, the Hamiltonian is something that we'll be meditating on quite a bit in this discussion. So in order to obtain the Hamiltonian, we need to identify momenta conjugate to both the scalar field and the gauge potential. Usually, what would you call the momentum conjugate to the gauge potential in electromagnetism? I mean, this is an exercise, but in electromagnetism and Yang-Mills theory, the momentum conjugate to the gauge potential is going to be the electric field, the 0I component of the curvature.
Oh.
And that's something that, so it's like saying the energy density, or the Hamiltonian in Yang-Mills theory, roughly is given by like E squared plus B squared.
Right.
And you see, this really has the structure of like p squared plus some potential. And this is just a sort of symbolic analogy, but if you did the analysis carefully, you would discover that it's actually going to be the 0I component. That's going to be the conjugate momentum to A, usually when you fix temporal gauge.
See.
So this is an exercise to check. And remember that the spatial odd star of the field strength is the magnetic field. And the same thing is true here. But note that these are not electromagnetic fields, literally. They're not U1 fields. They're SU2 fields, right? So it's an SU2 electric field and an SU2 magnetic field. And this is important to demarcate because later there will be an actual U1 electric and magnetic field also because of spontaneous symmetry breaking. So the first relation for the scalar, like for the scalar momentum, is pretty simple. I mean, it's very analogous to what happens in mechanics. It's like the velocity is related to the momentum. And then if you did the Legendre transform, you discover the Hamiltonian to be the following, right? So you're going to have two p squared, like momentum terms. So there's the E squared coming from the gauge field, and then there's going to be pi squared coming from the scalar. And then as we discussed, there's a B squared coming from the potential for the Yang-Mills fields. And then there's going to be di phi dot di phi plus V for the scalar. Now, why we're interested in the Hamiltonian is because we want to understand vacuum configurations that minimize the Hamiltonian, right? And so from just looking, you see what they should be, right? So vacuum configurations ought to be the ones that satisfy these conditions. You want to have minimum, you want to have like d mu phi being 0 so that you have no pi and you don't have any spatial gradients. You want all the components of the gauge field, the curvature of the gauge field to vanish, and you want V to be 0. So just keep these in the back of your mind because it'll be important for what comes next. But remember, the magnetic monopoles we're interested in are still electromagnetic. I mean, they're still those of U1 Maxwell theory. And we want to find them. And if we want to find them, we first need to, spontaneously break the symmetry from SU2 down to U1. Really, let's see if I've gotten this correct. Yeah, so the SO2 is just at the Lie algebra level the same as U1, but what's easier to visualize is how the SO2 is embedded in SO3, right? The idea is, you give me a vector, right, in three-dimensional space. Vector is not going to be SO3 invariant, but it's going to be SO2 invariant, right? It's going to be invariant under the rotations along the axis. So that is what happens when we choose solutions satisfying all those vacuum conditions we identified that are given by some constant vector in this internal three-dimensional space. Right? So it's like saying I take a vector, any vector, honestly, in three-dimensional space, and the rotation symmetry gets broken down to the rotations around the vector, basically. For convenience, we'll take the z-axis, like a vector along the z-axis. And remember, this is so E hat 3 is a unit vector in internal space. This is space-time scalar, and now it's literally space-time constant. What is it, Pratyul?
Is it something like you're fixing your angular momentum along a particular basis, and if you look at any sort of system, you can kind of find one basis, or is it?
Oh, it's simpler than that. It's like saying, I mean, it's literally like saying you have space, right? Empty space in three dimensions. That's rotationally invariant, right? If I had a point there, then that's rotationally invariant under all kinds of rotations, right?
Okay.
So the point, imagine, is the origin. But now if I have a vector, obviously the vector is going to rotate if I, just did random rotations. But if I rotate around the vector, then
Okay, cool.
I'll still have
Yeah,
the
okay,
symmetry.
yeah.
So that's why the full rotation symmetry is broken down to just rotation around one vector. And for simplicity, choose that vector to fall along an axis of the space, and we'll choose the z-axis. So that's the basic idea.
Okay.
Cool. So now this field satisfies phi dot phi is a squared. Just, by definition, I mean, v has to be 0. V was phi squared minus a squared whole squared. So this has to happen. Again, keep that in the back of your mind now. Okay. So this is an exercise for you guys around this background, right? The background where the gauge field is 0 and the scalar is given by a fixed vector. If you were to perturb, like if you were to add fluctuations, then you'll obtain the following spectrum, meaning you'll have a massless gauge field, you'll have massive gauge fields, and you'll have a scalar, right, which have the following masses and charges. This is like the basic exercise you go through when you are first introduced to the Higgs mechanism. So this is something that you guys should try. Now, why would that happen? So you see you have two of these massive, so you see the two massive gauge fields plus the massless one were in all the O3 gauge field in the unbroken theory. But when you break the symmetry, then one of them remains massless and the other two gain a mass. Right? This is very much like what happens in in electroweak theory, if you think about it. But of course, electroweak theory is SU2 times U1. And so what happens is that when you break, you don't just have W plus W minus and the gauge field, like the electromagnetic gauge field, you have W plus W minus Z and the gauge field. Right, so you have W plus W minus and Z that gain a mass, and then you have the electromagnetic gauge field that's massless. So this is basically a simpler version of that phenomenon. And remember, the W plus and W minus have a charge. So I encourage you guys to work this out. And just out of curiosity, I mean, do you see why the mass of the scalar goes like the square root of the coupling lambda? Remember, lambda was in front of the potential, right? I mean, it's just because you're Taylor expanding some quartic function and you're going to get some quadratic part. The part that's quadratic in phi is going to be, the master. And so the coefficient is going to be something that depends on lambda. Right? So that's sort of the idea. Cool. And also, another interesting thing is that the massless electromagnetic gauge field is the constant vector A dotted with W. We'll see that come up again. So now let's just talk about finite energy solutions, right? We talked about vacuum configurations, but now let's talk about solutions that have finite energy. What does that mean? It just means that if you computed the energy as the integral of the Hamiltonian, then you get a number that's not infinite. So if you want that to happen, you want the integrand to be such that it decays as you go off to infinity, right? And so basically, the Higgs field will approach vacuum configurations as you leave a certain radius, right? So that's the intuition that we'd like to make precise. So you have some space of Higgs fields, right? So you have gamma, which is a big space of fields, all of which solve the equations of motion, right? So that's the biggest space. And now what we want to do is characterize those configurations for which there's, the field is non-zero up to some value, like up to some radius, and beyond that radius it's just 0, right? So, literally what's going to happen is that phi of, so if I take phi to be constant, right, then this space, this otherwise infinite dimensional space, is just going to be R3, the internal space. right? Because the field space is R3 at every point. But then if I have constant fields, then it's like having just one R3. And really, what I want to do is think about the potential as a function from the field space to R, right? And I want to define, you know, this M naught as the sort of sphere, right? After which V is, V is zero. Basically, the Higgs field reaches its vacuum configuration. Note that M naught is itself going to be a two sphere in this R3 of constant configurations, right? So now let's see. What I have is these phi infinity of r hat, as I call them, which is basically the limit as you take r to infinity of the field configuration phi. And those, as we know, for finite energy configurations, have to belong to this curly M naught, right? Because I want V to be zero, right? If I take phi and then plug it into V, it has to be zero. And that is a sphere, right? M naught is basically a sphere. And so you see this phi infinity is a map from the spatial infinity sphere to this M naught sphere.
So are you trying to do a stereographic projection here?
No, this is just,
Okay.
no, I mean, I'm not trying to put coordinates on the sphere. It's just
Okay.
identifying what
Mm-hmm.
it is. And there's a mapping between two spheres, right? One.
Okay.
But the point is that
Mm-hmm.
one of these spheres is in field space and the other sphere is in like space,
Okay.
right?
Okay.
So you see, this r hat is really coordinate on spatial infinity, which is this big sphere. And then M naught is a sphere in field space, which is what you get by evaluating phi infinity of R. Now, we have a certain topological number, which is the degree of phi infinity. And that's defined as the pullback on to real space of the volume of the field space sphere. And the pullback is with this phi infinity map. And this is a topological quantity. It basically counts how many times one sphere wraps the other sphere. Right? It's like saying how many volumes of of one sphere does the volume of the other sphere count. Right? That's what it means for. It's basically a higher dimensional version of a winding number, which, as you recall, is a map between like circles. And we'll see that this quantity plays an important role when we go further. So furthermore, let's restrict to like static solutions, right? So static solutions have also the momenta being zero. And the momenta, as we discussed, for the gauge field is the electric field. And for the scalar, it's the pi, the momentum conjugate to phi, which is like d naught phi. And basically, if you take static solutions, then the action just reduces to minus t times the Hamiltonian, the integral of the Hamiltonian. Right? So t is like the time interval that you've evaluated the action for. And so solutions that minimize the action actually minimize just the energy if we're talking about static solutions. Right? And this is what the tHooft-Polyakov ansatz aims at finding. It aims at finding solutions of the equations of motion which are static, right? And as such, they minimize the energy. Right? Cool. So h and k here are arbitrary functions, and this is the ansatz they make. And basically, if you wanted energy to be finite, you'll get certain asymptotic conditions for k and h. And if you really plug those those conditions back in, then you'll find that phi infinity has to be the simple function of r as you take r to infinity. So this is a little exercise for you guys to figure out the details, but it's pretty straightforward. You know, you have the energy, you know what function it is, you have static configurations, and you have an ansatz for the scalar and for the gauge field. So you just have to figure out what happens to the integrand as you go to very large radius.
So we're basically plugging this back into the energy density and trying to.
Exactly.
Okay.
Yeah. The energy density with like pi equals 0 and E equals 0.
Got it. Okay.
And furthermore, you can just solve the equations of motion with this ansatz. And you'll find solution. So, okay, first let me explain why you would want to do this, right? Of course, you might want to be thorough and find these solutions and, understand them. But really, the punchline is that the solutions exhibit a sort of exponentially decaying behavior, right, with space. And that gives you the impression of there being some object with a finite spatial extent, right? So there's a finite size to these solutions with a maximum Compton wavelength given in terms of 1 over the mass of the W particle, the W boson, or 1 over the mass of the Higgs. Right, so that's the point of doing this. I mean, the explicit solutions you can find numerically. I'm not sure you can even find them in closed form. But by doing the analysis very far, like at very large radius, you find this exponential behavior, which is important, right? Because this sort of exponentially decaying behavior tells us that the solution describes an object of finite size.
Yeah.
And, this is going to be our monopole. I mean, it would be no use if you found something that has the charge. I mean, I wouldn't say it's of no use, but it would be very weird if you found something that has the charge of the monopole, right? The quantum numbers of the monopole, but it's like infinitely extended in space, right? I mean, that's not going to do us any good.
Right.
So this is what the analysis of the equations of motion at very large distance is telling us. That these solutions describe finite size objects. Right? So now let's see if we can identify from our symmetry breaking solution something that satisfies that ansatz, right? I mean, we just discussed this in abstract. I just take static solutions and then I try to find something, right? So what we're interested in is moreover to find it within the symmetry breaking sector, right? Because that then we have some hope that it has something to do with magnetic monopoles. So let's take a close look at the U1 gauge potential that results from the symmetry breaking. Really, what it is the constant Higgs field dotted into your original gauge field, right, in the vacuum. And so F, again in the vacuum, because phi is constant, is just going to be phi dot G, where G is the curvature. But you see, it's only the components of the curvature along phi. Those are going to be the massless ones. Now that's interesting, right? I mean, think a little bit about why it's the massless gauge field, right, whose components are along the symmetry breaking direction. I mean, do you remember this motto from studying the Higgs mechanism that the gauge field eats the Nambu-Goldstone bosons? Right, so you see the ones in the other directions are actually, they gain a mass, right, by eating the otherwise massless modes. So the remaining massless mode is actually in the direction of phi. So that's sort of the trick here. So now we'll impose staticity, which means that the electric field is 0. But there will be a non-zero magnetic field. You see, this is the punchline. And we can find that. It's basically going to be given by epsilon dotted into r, 1 over r squared, basically in the direction of r. Right? And this is exactly the field we found, or we discussed for the Dirac's monopole. And we got back to it. But what? With magnetic charge 1 over E. Very curious.
Wait, can we go back to the form of gauge potential and how we arrived at that?
Right. So for that, if you really wanted to go through with the exercise here, you'd find it. And this is why I said that A mu is going to be A dot W. So where would that come from, you could wonder, right?
Right.
So let's take a look at the structure of the action.
Mm-hmm.
And look at the covariant derivative term.
Okay.
Right?
Right.
So you see that second term, that's where it'll come from.
Got it. Okay.
Cool. Good question. Now, let's try and see if we could be a bit more relaxed and ask about non-static finite energy configurations, right? All that analysis with the tOooft-Polyakov monopole is great, right? With the ansatz and, finding that actually in the symmetry breaking sector, it defines a monopole, and that's all very interesting. But let's just take a step back, right? And say, forget about staticity for a moment, just ask about finite energy conditions. What are they? The finite energy conditions are vacuum conditions far from some region, right? In sort of like large R, right? Close to spatial infinity, I have vacuum conditions for the Higgs field. That's what it means to be finite energy. And remember that those are basically that d mu phi is 0 and phi dot phi is a squared, right? It'll be useful to take the derivative of that condition. And then the reason why it's useful is that d mu phi being 0 means that partial mu phi minus 2e times w cross phi equals 0, which means that phi dotted with partial mu phi is actually phi dotted with w cross phi. Right? That comes from the first condition, basically taking the definition of the covariant derivative and expanding it. Right? So that's what I meant when I said also in the Higgs vacuum. That should be true. So the gauge potential is determined in all the directions except along phi. Right? And so you make the following ansatz, right? So in some senses, you're getting back to your question. So you have the determined part, the part that's determined by just the scalar field, right? Phi cross d mu phi. And then the part that's undetermined, which is phi a, right? Now, again, in the Higgs vacuum, we can find the field strength. And we find that that field strength is given by, again, two parts. One part that looks like the field strength of a U1 theory, and the other part that looks like some weird thing built from the scalar field. But really, there's a phi outside also. I mean, really, it's like phi dotted into that whole thing. So the field strength is along the phi direction in the Higgs vacuum. This is something that you probably want to work out. And you're going to have to use things like phi dot phi equals a squared and so on in clever ways in order to be able to simplify this thing. But now, okay, so appreciate that what we're doing here is we're actually finding the electromagnetic field strength as a function of the original field strength and the scalar, right? Now let's ask about the magnetic flux. So really, what is the field again in the Higgs vacuum? It's just phi dot phi f, right? Because f has no index in the internal directions. So that comes purely from phi, right? And then the two form, f, what I've defined here is f mu nu dx mu which dx nu, right? And if you rewrite the expression I had here, then with A, B, and C being the internal space indices, this is what I get. And so you see the magnetic flux is going to be given by the integral of df over some surface. Well, really over some volume, right? Or it's the integral of star with respect to space of f over some surface. And now you see, if something was d exact, right? There was some d exact contribution, it would drop out. This is why there's no magnetic flux in conventional Yang-Mills theory, because f is dA, right? And so you see, it's not going to be, well, we discussed this last time. If you wanted a magnetic source, f can't be dA. But then, you could go backwards. If you wanted non-zero magnetic flux, it's the same condition. If you had f equals dA, you're not going to get it. It's going to be 0. But you will get something purely now in terms of the scalars. Right? So that's the magnetic flux integral. And notice that this magnetic flux integral is independent of deformations of the vacuum. Right? So if you take deformations that preserve the vacuum condition far from the source for the Higgs field, then that quantity that we just wrote down is going to be independent. Which is another way of saying that this is actually a topological quantity. What is it, Pradyut?
What is deformation? Is it
So it's a
like
variation that preserves the two vacuum conditions.
okay, like what are the like
The
the
D
variables, like
DFI.
space-time variables, or I mean
No,
that is
so,
causing
so
the
you had
deformation.
two conditions, d mu phi equals 0 and phi dot
Yeah,
phi is a squared, right?
yeah.
Yeah.
So we're talking about field deformations, delta phi, that preserve these.
Okay. Okay. Good. Good.
Right? So it's basically like some delta which preserves those two conditions.
Okay.
So it's like a variation that's restricted to some conditions. So yeah, no, that's a good point that we want to clarify. So under variations that preserve, the finite energiness of the solution, you find that G doesn't vary, which is another way of saying that G is topological. And actually, it's just going to be the degree of phi infinity, which is something I told you to keep in the back of your mind. Right? So it's like this quantity, right? Phi dot d phi cross d phi is really the volume form on S2 adapted from R3. And the reason for that we'll go into, right? So S2 is a hypersurface in R3, right? And so really the volume form is given by taking pullback under the embedding of the contraction with respect to the normal of the volume of R3, right? So this all sounds very neat and geometrical, but explicitly it just means that if I took the contraction of the normal of dx which dy which dz, I would get the volume form on the sphere, which is x dy which dz, y dy which dx plus z dx which dy. And that's exactly what's going on with the phi's, right? If we were in the field space parameterized by the phi's, right, they literally form an R3 at every point in space. And then the vacuum condition phi dot phi equals a squared tells us that there's a sphere, and the condition d mu phi equals 0 tells us phi is constant. So it's literally just one R3, and then this defines a sphere of radius a squared, right? And then what's the volume form going to be? Well, it's
Is
just
it
basically this
radius A
formula.
or A square?
Sorry, is it?
Radius
Oh
A?
yeah, the radius will be a.
Yeah.
Yeah, sorry. So it's a sphere of radius a. And so basically, this is just an explicit version of that formula that we had before. So you see the magnetic charge is going to be, well, is a topological quantity. And the effect, what's the net effect of it being topological? It means that it's invariant under small deformations of the vacuum. And so we can ask, oh, well, what are those? There are things like time evolution, gauge transformations. and so on. So this is basically the higher dimensional version of the winding number of a vortex, which is the same kind of quantity. So in some sense, monopoles are like one higher dimension of vortices.
This is one question I've had, I've been thinking about. So, what kind of transformations actually preserve the topology of space? Or,
Well, it's literally anything that doesn't like imagine not puncturing the space or not creating some hole or some, not tearing it in half. So any small deformation you can imagine.
So
and
what
any
would essentially tear or puncture the space?
those are like, I mean, I'm not an expert in this, but I guess that those would count as some surgery operations or whatever. Like I change, if I'm going to change the connectedness of the space, if I'm going to change,
Right.
the fundamental group or something.
Ah,
So it's
okay.
like that would be what's beyond topological, but
Right. Yeah, I was just trying to figure that out in a physical context, like what would actually achieve that.
yeah. So basically, it's going to be some processes of, like monopole catalysis. You can imagine that would change the right, or some monopole is annihilation, or some crazy thing like that. That would really change the topology of the space, right, of the field space. So yeah.
Right. Yeah. So by monopole catalysis, you mean just come together of.
Yeah, I mean, I just mean imagine having some number of monopoles changing into another number,
Yeah.
some other number of monopoles.
Exactly.
I mean, I don't know exactly under what
circumstances.
Well, you see, the thing is that you have a clear notion of conservation, even here of numbers, right?
Right.
But you could have some, for instance, you could have some kind of confinement transition where monopoles all condense, right? And they all condense into dipoles or something. And monopoles themselves are like way too energetic to excite. And then your field space will look pretty normal. Right? It won't look like there's anything special happening.
Right.
Kind of like what happens in SU2 gauge theory in the standard model. It doesn't really look like anything's happening.
Right.
So yeah, but you see, there's a difference here. We're talking about the topology of field space, and then there's a topology of space, right? And the only thing that really can change the topology of space is some quantum gravity process, right? Presumably, don't know, but presumably some quantum gravity process. But
and
topology of field space is a bit different.
Yeah, and we're concerned about the topology of field space here because
this is like, degree on curly M naught.
Got it. Okay.
So, okay, what we're going to do next, I think this is a nice place to stop for now.
Yeah.
But what we're going to do next is estimate basically the bound on the monopole's energy and mass, really.
Oh, that's
and
interesting.
we'll discuss what's called the BPS monopole. And this will be our sort of gateway into a lot of interesting physics and some supersymmetry. So, yeah, we'll get there. For now, let's stop here.
Yeah.
Are there any more questions?
Did you have anything else?
I think it was.
No? Okay. I'm going to stop it here then.